To Embedded Internals. This is ninth episode of our series, Execution Awareness series. This episode is based on static libraries versus dynamic linking. We all know that our ELF does not contain everything like the printf, scanf, or all other library functions. Still, it runs perfectly. What happens at the runtime that even if the binary does not contain the libraries, still it is able to run perfectly on operating system. Before going in depth detail, let me just give the brief idea of the all previous episode we have done in this series. So, in the first episode, we wrote our first C program to print a statement like, in this case, hello world, welcome to embedded internals on output screen. In the second episode, we checked the life cycle of a Linux program, from source code to ELF binary to process to running program and then the termination. What happens behind the scene? In the third episode, we see the different stages of compilation like preprocessor, compiler, assembler, linker, and finally how we get the ELF executable. In the fourth episode, we see the what actually is inside the ELF file, how ELF is complete structured binary data, and how kernel understands the ELF file. In the fifth episode, we saw the program execution pipeline. What happens when you run any command, how kernel create a new process, how kernel loads the ELF, create process, maps memory, and starts execution. So, complete program execution pipeline. In the sixth episode, we saw what happens before the main function is being called. In the seventh episode is about memory layout of Linux program. What are the different memory segments like text segment, data segment, BSS segment, stack segment, heap segment? What is inside these segments? Why there are different segments? What happens when we crosses the memory regions? In depth detail. In the eighth episode, we saw the user space versus kernel space. Why there are two different spaces in the Linux operating system, what are the purpose of each, and how they interact among themselves. In this today's episode, we are going to see the shared libraries and dynamic linking. So, we all know that Linux uses shared libraries. Instead of embedding the all code inside a binary, we uses dynamic linking. So, linking at the runtime. Our program which uses a library like libc, which is standard C library in .so. .so means shared libraries, shared library, and that is being loaded at runtime. So this is the big idea behind using shared library. Why we use the shared library? First benefit we get is that our program stays small. So program size is very small compared to using static libraries. Second is that code is shared among processes at a time. So at one time, one shared libraries is inside the operating system, and all the formats like printf, scanf, all the different function is shared across processes. So every process is sharing the same code part. So these two are the biggest benefit of using the shared libraries. So shared libraries or shared objects. So anything which ends with file ending with .so, like in this case libc.so is shared object. We can say like libc.so, standard C shared library. C library. Similarly, we have like libm for maths .so. This is for math library. So our program depends upon libc, any shared library, and which can be loaded at the linking time, which can be loaded by the loader at the runtime for linking different libraries. Okay, we can see in the terminal, when you see the dependencies, so on which all libraries this executable depends on. You see, this depend on libc.so.6. 6 is the version which is linked with this GNU libc corresponding to some address. So our executable depends upon this library. Even we can say, when you check, you see shared library libc.so.c, and it is needed. Needed means it's without which the executable will not run. So this is an urgent need of this executable to run, which is to include the shared library, which is libc.so.6. So we see that our executable depends on some library, some shared library for uh, running, without which it is not going to perform correctly. Even the executable is complete, but during the runtime, it needs to load this library to run perfectly. So of linking, one is static linking and other is dynamic linking. In the static linking, when we say static linking, means at compile time. So we can say this is a self-contained binary, as it does not have any runtime dependency, no runtime dependencies. Okay. And what is create? So you get a large binary in this case, because everything is embedded into the binary itself, which make it self-containing, self-sustainable, but it also increases its size, so it has large binary size. Large binary size. One more thing, if there is any change in the libraries, or any new version or new updates has been done in the library, that cannot be included in the shared, in the binary which is created using shared linking, because otherwise we have to do the whole process again, update the library and then create the binary. Whereas in the case of linking, show no updates, we can write no updates from libraries, no update from libraries. So these two are basically cons of using static library, static linking, sorry. Whereas this is pros. Yes, your one binary is uh, sufficient, you don't have any runtime dependencies. Now let's check in the dynamic linking. In the dynamic linking, first thing, runtime dependency, because same library is being shared across different process, shared memory across different process. Runtime dependencies, like we have seen, this R executable is dependent on particular library to perform correctly, but it also reduces the size of binary, so small binary. And if there is any update in the library, which can be included, easily included. So easy updates of binaries. So easy updates of libraries. And what is the con? That is runtime dependency, because without the libraries, it is ELF will not going to run. S- uh, but today's in this time, most of the Linux program use dynamic linking because of small binary and all other benefits. So we can say that dynamic linking is a default linking in our Linux operating system. Okay. We are saying about the size of binaries. So let me create two binaries of static linking, one with static linking and one with dynamic linking. And by default we create ELF with dynamic linking. Okay, so normally we will have two ELFs, one is static and one is dynamic. See the difference in size. Static is such a large size binary, whereas dynamic linking, the size of binary is very small. So this is the proof. First thing is by kernel. So kernel loads our program. Once kernel load the program, kernel also load ld linux.so, which is dynamic linker. So kernel loads dynamic linker, which is in our case ld linux.so. So what is this? This is dynamic linker, and it's task of kernel to load this linker, which will going to further load our libraries. Now once the dynamic linker is loaded, it will load libc dynamic linker.linux.so will load standard library, shared library libc.so, which is our standard C shared library. This is standard C library. So who loads the standard C library is dynamic linker loads it, and dynamic linker is being loaded by kernel. So what is the task of our standard C library is to resolve symbols like in our case printf, and after resolving the symbol, uh, transfer will be given to program. So transfer control to program. First step will be kernel will going to load our program, and kernel also load the dynamic linker, which is ld linux.so in our case, which will load the standard C library, and the task of standard C library to resolve all the symbols included in the program. And after resolving all the symbols, it will transfer control back to our program. Can say that our program is actually completed at the runtime. I will show you what are the different. Say we have W is for undefined symbols. So puts means printf statement, which is a part of libc. Main function which main function which will be called by underscore underscore libc underscore start underscore main. We have detailed discussion of this uh, in our episode 6. uh, please check. And these are other constructions and constructor and destructor which are being used in our program. So they are the different symbols which has been included inside it. Okay, so we can say that during runtime printf is being included by libc.so. So libc.so knows the actual address. So in this case, or in the dynamic linking actually happens late, which means it is happening at the runtime, not at compile time. Okay, we need to understand PLT and GOT to know how the dynamic linking actually works internally. PLT, as we have defined, is procedure linkage table, whereas GOT is global offset table. Let us see what is inside the PLT and GOT. When we say PLT is used for functions call, act like a jump table, whereas GOT stores the actual address of function, which can be filled at runtime. Okay, so when we say PLT, so PLT will be used for function calls. Used for function calls. So GOT will give you the address. Okay, at this particular address, this function will resides, like at this address. Printf will be there. Okay, and from PLT we know, okay, this is the printf. Now we can move to the definition from this particular address. So GOT give you the address, PLT points to where the function call actually resides. Okay, so PLT is used for function table, so it is like jump table. You move to a particular library function and that definition will be linked at this table. So it is like jump table. Whereas GOT stored the actual address of function. So it stores the actual address of functions. So GOT stores the address, whereas PLT is used for functions calls. So it's and as it is dynamically linked, so the address will be stored at runtime. So it is filled at runtime. So flow will be program in our case is calling printf statement. Okay, now we have the printf statement. We need the address where this printf statement exists in libc. So PLT will act as a jump table for the to finding the printf entry in the PLF. When we find the printf entry, we should know its address. So we will go to GOT to give the address. Once we get the address, libc will be called at that address, and the function will got execute, because all function will be executed from libc only. So to reach the libc, we first need to know the entry. So PLT have the PLT is used for function call. It is like the jump table which has the entry of this function call. So from the PLT we get the entry of this function call, and after the getting the entry we will move to GOT to get the actual address of this function. Once we get the address of that function, we will ask the libc to reach at this address and execute this function. So, and libc will perform the execution part. Okay, so we see that PLT plus GOT is indirect layer for dynamic linking. Without PLC and GOT, dynamic linking will not be possible. So they both are indirection layer for dynamic linking. Indirection layer for dynamic linking. in D are executable. Let us see PLT. So we have the PLT section, which will be used to call the function call, which is put C. Let's see in the details. So this is main entry, global entry. So this is the disassembly of section.plt. Okay, .plt, which is at this particular address. So what is in this PLT is, so this is the disassembly of section.plt. .plt. Okay, so let's see, it jumping at particular int function, this jump at global offset of this table. Okay, and in the plt.got section we have, this is .got section disassemble. So we have one function called it jumps up to the particular function call. So plt is jumping to puts is like printf, which is the part of glibc.so. This is 1050 address. Okay, so like this puts.plt, you will see the function call which you are using inside your code. So this is how we can check the from where the our function is being resolved. So we have two type of bindings. Let move. One is lazy binding and other is eager binding. So what is in the lazy and eager binding is that lazy binding, as the name suggests, we are delaying the binding, whereas eager binding, so in the lazy binding we say that when you see the first function call, resolve the address at that point, and next call pe we will jump. So first time resolve function only when used, so we can say resolve function only when first used. First use time pe resolve and second use time pe we will jump. So we can say first call resolve the symbol, in the second call or the next call, then jump to the function, direct jump. So delay jumping is delayed. So two call. So in the lazy binding, which is the default binding actually, so we can say it is default binding. Default binding. Function is resolved only when it is first used. In the next call, direct jump is done. Whereas in case of eager binding, all the symbols are resolved at startup only. So no concept of delaying resolve. All symbols are resolved at startup. So it is like LD bind now. So at the startup only resolving is done. So we can say that as all the symbols has been resolved At the startup, we don't have to wait for a first or the next call. In the case of lazy winding, we have seen the improvement in startup speed. Improvement in startup speed, because we are not doing the symbol resolution at the startup, so it is improving the startup speed. Improves startup speed. Okay. Here the symbols are being resolved at the startup time, so startup speed is comparatively slow. And we all know that in case of dynamic linking, only one copy of libc is in the memory at a time, because all the process share the same binary. So it saves the RMX and also improves the execution. So we can say the dynamic shared libraries are for memory optimization. They also optimize the memory. Shared library means memory optimization, as at a time only one libc is in the memory. At a time only one libc.so in memory. So all process shares same libc, shares same shared library .so, which will going to improve the uh, speed and saves RAM. Memory optimization will be done and RAM size will be same, and execution will obviously be faster. Okay, faster execution. So this is the benefit of using shared library. First is we don't need multiple .so in the memory. All process will going to share the same SO, which will saves our RAM size, and execution will be faster. We have seen the library dependencies like of this ELF file depends on this library. Let us trace the loader. We are saying that the runtime loading is done. So let me show you what are steps is happening while loading by the loader. Okay, dot slash c. When you debug this, you will find that first step is it is finding the .so so it is finding the library. After it search the cache slash etc, then file search. Once the library will be found, it is calling that library, and then after that it initialize the program and transfer control to the program. So kernel loads the program, kernel loads the dynamic linker, that will load the library libc.so, and then program will be initialized and control will be transferred to our program. We have seen the execution, the same is described here. So control is being transferred to program is being run, which is to print a particular statement, and after that it is calling fini. So it is calling this to terminate the function. So function is being terminated, this link library will be not will be removed. So we have seen how the loader actually loads the program. It searches the libraries and do the loading. We have seen the symbol tables and we have also seen the PLT statement. Now the question is, what if the libraries are missing? There are some time as executable needs library, but libraries are missing. Library is not found. We usually get a runtime error. Runtime error, that is error while loading shared library, and ELF execution will stop. Error while loading shared library. What we have to do in this case? You run a executable and you find this error. This error indicates that libraries are missing. The important library which is needed for the program to run is missing. So what will you do? First is install the library which is missing. Okay, install the missing library and set if libraries you check, okay, libraries are also installed, still we are getting the error. In that case, set the path correctly. Set the path in the environment table correctly. Like we usually do, we export the library path. So export ld library path, wherever the path is. Okay, wherever the path is, set the path. So whenever the library will be missing, we found some problem, try these two steps. Now we see the lots of benefits of having the dynamic linking. Is there any security issue or security risk of dynamic linking? Yes, there are some. So we can say security. First is that dynamic linking, library hijack is the problem. Anyone can hijack the library. Sometimes version mismatch issue we have also seen. So we need to use the current version which is required by the program. Current version library should be available in the OS. So version mismatch, library hijacking. So we need to prevent this. We need to have the correct R path, and we should use the secure loader paths for dynamic linking. Okay. So at this point of time, we see that our executable is not complete program. It depends on runtime linking for its execution. So we usually say ELF is complete program, but ELF or executable is not complete program. It depends on dynamic linking or runtime linking for its execution. So this is the service dynamic cut. So which completes our executable is dynamic linking. Without library, ELF will not going to work. So this is for this episode. We see let me give you the quick review of this episode. We see that how our program is not a complete let me give you the quick review of this episode. We see that our executable depends on shared libraries for execution, which is resolved at the runtime. So our program depends on glibc.so, which is shared library loaded at the runtime for its operation. Now, what is .so? .so means shared library, which can be libc.so or libm.so, different types of. We have seen dynamic linking and static linking. What are the benefits of those both, and the cons of both? We have seen the execution flow, how our kernel loads the program, kernel load dynamic linker load C libraries which will resolve the symbols, and then the transfer is controlled to the program. We have seen the similar execution from the terminal command as well. We have seen what is PLT and GOT, how PLT is used for function calls and act as jump table, whereas GLT knows the GOT knows the actual address of function which is filled at runtime, and its corresponding program flow, like our program is calling the printf, it will go to PLT entry to find the printf function called definition, and then we will find the address of that in the GOT table, and that address will be used by the libc to execute the function. So PLT and GOT both are indirect layer for dynamic linking. We have seen the lazy binding and eager binding and its benefits, how the shared memory improves the memory, so it is used as memory optimization technique, how it saves the RAM and makes a faster execution, what happens when the library is missing, what kind of error we get and how we can resolve those error, and what are the security risk of dynamic linking. So at the end I can say that ELF is not complete program, but it depends on runtime linking or the shared libraries which is resolved at runtime for execution. Thank you.